Good afternoon. I think everybody here knows me, but if there's anybody watching who doesn't yet, I'm Patty Mabry, the Executive Director for the Network Science Institute. And we are here today to have one of our network science talks from Nitesh Chawla. It's going to be an exciting talk, but I am not going to actually give the introduction. We're going to let Anne McCraney do that from my uni. I'm just going to tell you a few exciting things we have coming down the pike, mostly that on Tuesday, November 14, anybody who's interested in the multi-omics phenomena, we are having a meeting up in Indy at Goodman Hall, 12:30 on the 14th. Now, those of you who are interested in this topic should have gotten an email already, but some people may be interested that didn't know about it yet. If that's you, let us know. Either myself, we have Lourdes sitting in the back. Lourdes, raise your hand. She's raising her hand back there. We can get you an invitation to the meeting. We just didn't want to bombard everyone with it. Okay. The other thing we're going to have at some point is all of our research scientists will be having a day when they present a little bit about themselves, and we'll let you know. It looks like that's probably going to be sometime in the spring semester of the 2018, January, February, March timeframe. So I think that's it for now. Oh, and then we have another network science talk on, okay, it's December the 4th. Anna Mueller will be coming, right? Did I get the name right? Okay, so those are the things we have planned. But as always, if you're interested in a open science forum where you come and talk about any of your interests or going for a funding opportunity or anything like that, just let us know and we can set that up for you. And then you can have a whole audience to talk to and bounce your ideas off of. Okay, without further ado, I'll have Anne McCraney come up and give the introduction.
So if you are interested in that or any of the other activities that we have and you're not already on our mailing list, you can send an email to iuni@indiana.edu and we'll be happy to add you. It's pretty limited circulation account, but we do send reminders for talks and things. And one other thing that we do have coming up, I believe on November the 6th, we're going to have a open science forum, December the 6th, an open science forum on the Awesome tool. I think we have said that, so we'll be sending reminders about that. So it's my pleasure to introduce Dr. Nitesh Chawla, who is the Frank Freeman Professor of Computer Science at the University of Notre Dame, up the state from us. He drove last night. He missed all the tornado warnings, which I'm impressed about. We missed none. But he has a really interesting history. So you got your PhD in, he got his PhD in computer science and engineering, then left academia for a while to be a banker, then had the good timing to come back at 2007 to leave banking and come back. He was in Canada, he tells us, so this is, he wasn't affected by our downturn, but came back to academia in 2007, has very quickly established himself in his research career here. He accomplished that, as he told us, by working lots of nights and weekends writing papers while he was still a banker. So it's very impressive to get back to academia after taking a detour. He is the director of Insenza. Am I pronouncing? Isenza, excuse me. I'm getting the pronunciation. So the Interdisciplinary Center for of Network Science and Applications, which actually has a very similar kind of mission in terms of interdisciplinary research as what IUNI has, a different structure, but very similar goals. And their center and his work in particular focuses on this intersection of data science and networks and machine learning, but there's lots and lots of different application areas that they have. Dr. Chawla himself has a lot of interest in using big data for the common good and for societal good. So I think some of that should come through today, but also in much of his other research that he does. In particular, a lot of his research on healthcare analytics and how to actually take what you've learned and use it for practical applications. That's amazing. Always impressive to hear that. So without any further ado, I'd like to introduce him and have him give his talk today. So thank you.
Thank you. Right. This is on. Yes, so thank you again for having me over. It's, gosh, I've gotten used to staying at a Biddle Hotel as well. So IU feels like a second home. There's so many friends here. So thank you again for having me back. And I planned my arrival last night because I knew there's a tornado coming, so I left late. And no, I didn't. So it just so happened I came to the morning and I was told there was a tornado warning yesterday. But I hope you all survived that well. And so I'm going to sort of give sort of a flavor about the stuff that we are doing on our recent work on higher order networks, and sort of give you a few applications and use cases. I won't quite get into some of our applications in healthcare, but feel free to ask questions as to what we may, what are some of the areas and techniques that we are focusing on. But first, I'd like to share with you of what we are trying to do with iCensus. Right, as Anne mentioned, that it's similar in many ways to the Network Science Institute here at IU. And what we sort of formed it back in 2007, 2008. It was a College of Science Center first, and then in 2010, 2011, we sort of petitioned to make it a University Research Institute, and it's extremely collaborative. So we're sort of driven by the idea of that grand challenge problem statements don't come to you and say, I'm a computer science problem, I'm a physics problem, I'm a sociology problem. Right? So it's we who create these disciplines around these problem statements, and then we sort of get ourselves siloed in departments. So one of the things that our iCensus has been is that we'll basically have these thematic problem statements that will, and those are what the students, postdocs, faculty, PIs, etc. would work on, and we sort of galvanize around them. So in fact, the location that we have, and we are hoping to expand it, it's sort of co-located where students from different departments sit there. Faculty, you don't have as many faculty offices as of now, but we have myself, physicist Zoltan Torochkai, sociologist David Hake, and Omar Lizardo, and then the physicist Dervish. So we don't have offices in our home departments. I don't have an office in computer science or College of Engineering. My office is in iCensus, and the students from different departments co-locate. And that has led to some unbelievable science. Because that co-location, when you have these hallway conversations, leads to magic. And what we realize is to have a good life as a faculty member, let the students co-locate and just sit back and watch the fun, right? So that's a good outcome of having an institute like that. And some other things that we've been driven is that we are focusing on the algorithms. So it is a technical center. We are focused on algorithms, technology, techniques, methods, but we are driven by some of the applications that we are trying to drive. And we are focusing on significant applications from a society aspect. So I'll talk about at least one or two of those applications in the talk today, but ranging from healthcare to, and we don't have a school of medicine or public health, but what we have done is developed a collaborator with the hospitals, clinics, independent living facilities, high schools in South Bend, Indiana. And that's led us to think faster about translation, because those folks are not driven by a grant or a paper. They ask the question, how can it help me improve my practice or help establish this with the patient? And significant involvement with industry as well. We have a very healthy research portfolio from industry funding. And as I said, it is very interdisciplinary from the core. So that's what sort of leads us to the new challenges. And in fact, the talk I'll give today, the paper that we have, which is a method, technique, algorithm, was driven by an application area on tackling invasive species, looking at shipping network. That application made us think about that we are doing networks wrong, and we should rethink networks in many ways. And that's what led us to this work and the student's PhD dissertation. So there's an exciting element of what application layers can bring to us as from a fundamental research perspective. But again, I'm teaching this to the core. That's where, the Center for Complex Networks here and the Institute of Network Science is sort of, founded on the similar principles. So one of the things that, when we think about networks or the work that I'm going to talk about today is, if we look at the world, we are living in a complex world, right? Whether we think about it as a trajectory of vehicles, and network scientists and data scientists have looked at that data. Whether we look at flow of information, whether it's the fake news work or the misinformation work that IU is at the frontier of, we have looked at it from a networks perspective. Spread of disease, epidemiology, etc. We have looked at it from a networks perspective. So truly things are connected. It doesn't matter what domain one may be in, but graphs or networks provide us a compelling viewpoint to that area, viewpoint from that perspective. So this is how the world comes to us in, right? Then we try to derive a network from this world, right? So network is an abstraction, right? The world isn't saying, hey, I'm a network, I'm a graph, this is the vehicle, this is the trajectories, that's how the world is. It's a complex world from that. And then we figure out what are the interacting components, how they may interact with each other, and then we say, hey, this is how the network could be created. So network in many ways, when we begin to look at it, when we begin to develop our algorithms at it, we are a step away from the actual real world, the complex world, because we have created a representation, we have created an abstraction of it. So now the challenge is that if we have created an abstraction of it, and then we go through so we look at this data, we create a network, and we do the analysis, and we write a paper, and we celebrate that story, right? So now there's something could go wrong. There's only one thing, if our analysis algorithms are correct and we prove it, we establish the math behind them, we are collecting the data, that the way it's coming, whether it's phone call cascades, traffic movements, web click streams, etc. What if the network representation is incorrect? Because remember, we have taken this world, we have taken the raw data, and now we have built a network out of it. And we now do all the analysis, we make all the observations based on this network. What if we erred on the side of building the right network from this data? And oftentimes in academia, we don't even have raw data. We go to a place like Snap or some other place and we download the networks that somebody else created. So we are missing a step between, hey, does that network represent the underlying phenomena correct? Right? So let's take a look at the way we do network is the shipping network over here. Right? If I look at this, I have, and this is the actual data we have. So for another of our NSF funded grants, we are looking at invasive species and how they move around in the world. And as a result of that, we collected, we leased data from Lloyd's Maritime Insurance Unit. So I have data about every ship that's left every port in the world, what time, when they left, what kind of a ship it was for the last 10 years or more. So we have that entire ship movement data. So we look at the ship movement data, the kind of vessel it is, and I look at, okay, the ship goes from Tokyo to Singapore, goes to LA, and I typically build a network like this. I say, okay, what's the movement? But these are the two nodes on my ports. Hey, a ship goes from Tokyo to Singapore, there's a connection. I can create a weight. And then I say, okay, from Singapore, a ship goes to LA, and I can create an edge, and I can weight it based on the traffic, and I can build my network by using a first order network approximation, right? That's where typically most of the networks have been built. We basically look at A to B, build a connection, and move on. However, one may think about it slightly differently is, what if the ship leaves Shanghai, goes to Singapore, but whenever it comes for Shanghai, it is more likely to go to Seattle. When it comes from Tokyo, it is more likely to go to LA. That piece of information on how the original data was intended to show it is missing, because now we took this data, we converted it into the network the way we would do using a first order Markovian assumption, and we built this network, right? There's nothing wrong in an assumption from that perspective. However, it's not really representing. And why that is important, let's say that for the sake of an assumption, that the species found in the port of Shanghai pose a risk to Seattle differently than they pose a risk to LA. Species found at the port of Tokyo don't pose a risk to either of the two places. Now, the ship leaves, and if you're basically looking at this network to study invasive species, how species are moving, and I'll talk about that application a bit later, not understanding that this ship actually originated from Shanghai versus Tokyo, my risk estimation of invasive species is going to be diluted, because I missed an important piece of information that the species that were in Shanghai are going to pose a bigger risk to one of these ports. And in the US alone, invasive species is $120 billion annual loss. I mean, the Lake Michigan, etc., zebra mussels, Asian carp, etc., and they can all be traced back to the ship movement traffic. So that's sort of the underlying issue of the problem statement that we're looking at, and then make a bold statement here, but yes, we have been building networks incorrectly, and we have seen that even in systems biology, where I can change my network assumption, and I can come up with an entirely different conclusion that suits my research hypothesis. Just by, not that the network is wrong, I'm changing the assumption the way I'm building it, or I'm not looking at, we can look at it from a page, a web page clickstream data is another example. If you're building a network based on my clickstream, I start from a point A, that leads me to B, and then I go to C, I go to another page, D, and then finally I find something at E, and I stop and I move on. So if I just look at my network D to E without understanding I actually started from A, an important piece of my trajectory on how I was searching for information, what led me from where, is missing. And this could also be applicable to the fake news proliferation and et cetera, where the source was, because we're doing multiple shares. How it originates, where it originates from, can quickly get lost in the mix. And so we don't know where it actually began from. So it can be sort of big. Disease spread as well has the similar issues. So can we sort of think about it from that perspective and see how we build these networks from the raw data to capture the underlying dynamics, to capture what way the components are interacting with each other. So this is the work on the higher order networks that we was talking about. And again, this is the data set. My student loves this video, so I'm just going to have it because I promised him I will. So bear with me. I don't know what it does. It does some cool things. So basically, if you think about this, is the ship movement traffic according to Gian. And it's from an actual data where he's basically plotting the movement of ships from Shanghai to Singapore to LA. So basically what you're seeing on the right is the way I would construct a network: Shanghai to Singapore, Singapore to LA. Then there's another ship that comes. I create that link, Singapore to LA, and so on. And I do the same thing to Seattle, and I do the same thing from Tokyo, etc. You get the gist. You should have accelerated the video, right? But so this is the first order network construction that I would build. And in fact, our first work on this, when we first published a KDD paper on this study, we built it this way. And we celebrated our paper as understanding invasive species using a species flow model, etc. And now we are basically saying that, hey, maybe we modeled it wrong because we did it this way. And then we sort of go on from there. And then other thing that I'd like to think about is that if we are thinking about the higher order network, the way we are conditioning it now is that I'll split my Singapore node. Right, so this for folks who are familiar with metagraphs, etc., this may be akin to that, but it's very different. And I can answer when we go to the technical details. I can talk about it. But when we build the higher order network representation, what we are showing here is Singapore conditioned on Tokyo. That's what the data tells us is more likely to go to Seattle. Singapore conditioned on Shanghai is more likely to go to LA. So this is sort of the higher order, this is the true data representation that we are trying to go after within our network, right? So now in this case, instead of a first order, we're looking at a second order. And there was a 2014 paper by Roswell et al. In Nature Communications where they talked about second order Markovian representation of using these networks. And we are going beyond those with our work that was published last year. So we have this Singapore given Shanghai, that's the trajectory, Singapore given Tokyo, is the subsequent trajectory, right? So this is the problem that we are trying to solve in summary, as a statement, that if my previous first order network looked like this, which clearly is not an accurate representation of the underlying data, because if it's the ship movement traffic from Singapore onwards is conditioned on where it came from, depending on where the ship, or the probability or the likelihood that the ship movement is conditioned on that. Why that's important? Because we are trying to look at the ships as being the carriers of the species of if it's a human being or a disease, etc. Right? So depending on where it came from, if there's an epidemic here, there's a species here which poses a risk to Seattle, I need to get that better because I can apply the intervention accordingly. I missed that information over here. So what that could mean is I apply a heavy intervention to Singapore, which can be more costly, versus I can step back and say, hey, if a ship is coming from Tokyo, I'll apply this intervention. If not, don't worry about it. Because Shanghai is not posing a risk. So it can lead to a more cost-effective reduction, and especially when one is trying to do invasive species management, these ports are privately managed. So they're they're corporations, they're enterprises. And you have to make a business argument to them about a policy as well, from that perspective. And so we are trying to see if we can build something like this over here and figure out the traffic patterns. I don't know what the ship movement is. And of course, there is some likelihood still of going to LA, but but we are more interested in seeing what these dependencies are. Now, in this case, I'm only showing you the second order dependency, but it could be there's another port here. So then we keep expanding these nodes. Each of these nodes gets split and gets expanded into different nodes. And the challenge that we sort of had is, let's say we build this higher order network representation. Do I now need to go in and change every algorithm for my network analysis and science and things? There won't be an appetite in the community for that. So we wanted to build an abstraction, a data structure, if you will, which scales, and we now have a parameter-free version of this as well, which scales and is also amenable to the network analysis toolboxes, which means take your community detection algorithms, take your page rank algorithms, etc. Nothing changes over there. So the structure would work with the existing algorithms. Only thing we are changing is how we are representing the data in the network and how we are changing the edge weights. So this was, as I said, the original, going beyond the first order network work was by Roosevelt et al. In 2014 in their Nature.com paper, and where they sort of made a compelling argument and case for us to think beyond the first order network. And they looked at the traffic patterns as well. They looked at bigrams, they looked at trigrams, and these figures are from their paper. And then they constructed a second order Markov model, where they basically said that first order from Seattle to Chicago, Chicago to New York, Chicago, Atlanta, but there is these more dependencies that may be existing that will not be captured by just looking at a first order network. And they stopped at the fixed second order network representation, because they state in their paper that higher order Markov models are more complex due to combinatorial explosion, which is a given. So they sort of presented a problem statement, and then they have a very nice solution for a fixed second order network representation. And what we sort of wanted to really, again, go back to do is, there could be more than two orders, and in a complex world, in a complex system, different components may be carrying different orders of dependency amongst each other. There could be some components which satisfy first order. There could be some components which satisfy second order. There could be some that satisfy third order. So we cannot impose a fixed structure, a fixed dependency among these network nodes or components, because that may not be the case, because we are trying to represent scenarios that exist in the complex world, which are not predictable in many ways, which could be unprecedented in many ways. Right? So how do we sort of build those things out to build it? And we wanted to use it, and we wanted to make sure that it's accurate, it's scalable, and it's also amenable to the existing tools as well. So to give you an idea is the variable orders that I'm talking about. So this is the figure where we talk about Shanghai to Singapore, Singapore given Shanghai. It gets split, Singapore, there's no dependency otherwise. Singapore given Tokyo, then Singapore given Tokyo, Busan, Tianjin. Tokyo is conditioned on Busan and Tianjin, so there could be multiple higher orders that we could discover just based on how Singapore is interacting with the node before and how Singapore is being split. So we have to be able to capture and discover these from the data. So as I said, last year, the first work that we published on this last year was the higher order network algorithm, it was in Science Advances last year. And we sort of looked at it we still had a couple of parameters in that work, and the work that's under review at www this year eliminates the parameters and makes it much more scalable space and compute perspective. So we had the raw data. So we said, okay, there's four things that we need to do. There is a raw sequential data given to us because we had the luxury of the shipping data, and then we also have the luxury of, say, cell phone communication data when we're looking at Cascade, so we know how the raw data exists, right, from a ship movement, etc. And then we extracted rules where we looked at which nodes need to be, and if we just build initial instantiation could be a first order network, and then we basically see that, okay, should I go beyond the first order for each node? So we create rules and we decide which nodes to split into higher order nodes and which nodes do not. And then we rewire the network, and then we create an abstraction which we say, now you can use it the way you see fit without changing any of your underlying analysis algorithms. And higher order organizations have been explored by other folks as well, but oftentimes it's required higher order for this particular application, for this particular algorithm. Let's build a new community detection algorithm, if you will, to discover the higher order structures and organization in the data versus using a more a generalized framework. So as I said again, so we have the raw sequential data available to us of the ship movement, Tokyo, Singapore, LA, etc. The example that we have seen, and then we counted subsequence of various orders. So we sort of did a play on the association rule mining algorithm in data mining, where they look at support and confidence of item sets and how they co-occur. So it's not quite, we're not doing association rule mining, but think of that as a concept. If you study that in your data mining or data science class, calling it data science is more fashionable nowadays, so we call it that. And then we do the count the subsequence, and then we create a probability distribution of the first order. And then we create a probability distribution of the second order as well, where we basically look at, okay, let's add another sequence step to it. What happens to my probability distribution as I'm moving? And then once we have done that, we can compute, we can build rules out of this. So Shanghai given Singapore, then Singapore was going to LA and Seattle, and then I conditioned that on Singapore given Shanghai. And now I'm beginning to rewire my edges to reflect these transitions. And then one thing else that we do is when we actually build these probability distributions, we compute, we have a minimum support threshold parameter that we have set, that the support threshold parameter is a monotonic function, and it sort of is a function of what's my distribution prior to the existing one, and we compute the KL divergence from that perspective, and we see is it significant enough for me to have a second order. So every time we make a decision to go from lower order to a higher order, we establish whether there is a statistical significance in establishing the higher order. And if there is no statistical significance.
So you talked something about coming up with the priors, and then you do the K divergence on the priors, right? So how do you come up with the priors?
Not the priors, on the conditionals. Basically what we are doing is on the marginals, conditionals. Yeah. So we basically do, and then we compute, then we compute the KL divergence on the probability distributions, and we have a minimum threshold that we have set, and we see if it's sort of exceeding that minimum threshold, and we go on from there. Now, of course, so those were the parameters that we had in this algorithm, and those are the parameters that we have eliminated in the new version of this algorithm from our last year's paper to this year's paper. And just to give you an idea, so of course, one challenge, of course, arises is that as we go from a conventional first order to a higher order, my number of edges and my number of nodes are obviously going to increase, right? So yes, it's going to cause an increase in the space of my network representation from that perspective. Oops. So that's something that we do need to think about is a space, but it is, the interesting thing is, what I'd like to point out here is the growth of it from second order to 5 order is not that significant a jump. What that means basically is because of the variable order that we're discovering from the data, not all nodes need to be 5 order. Some nodes may stay as first order. And if we compare with the Roosevelt method of the fixed second order, that gives you a much bigger, much more densely connected graph than we have with this. Of course, the number of nodes is smaller, but the growth is contained because not every node and the interaction has to be a higher order. If it's a first order that suffices to represent the data, that's what we leave it as. So the HON plus is the parameter free and scalable for arbitrarily high order. So we have the entire source code available via the higher order network website. So that source code has the new version of the algorithm. So if you were to download it today, you'll get this one, even though we haven't published it yet, but that's the source code that's available from the higher order. So as I was talking about, as we're building all these dependencies, right? So I go from the first order, second order, third order, etc. As the actual dependencies that I need to explore is a shrinking set, because the likelihood of the fifth order being a statistically significant dependence is going to get lower and lower as I go. So this is a shrinking set. So if there's a way for me to trim my search and not go beyond my second order and only go up to my second order or third order if it's needed, then I can do really well. Because what's happening with right now is I'm actually exploring all the possible orders and then I prune back. So I'm doing post-pruning, if you will, in my search space versus doing a pre-pruning where I basically say that I should not go beyond my second order if it's not relevant. But now in this method, we sort of go, which sort of really has from a space issue as well. So our question was, how do we now begin to optimize it in terms of space and storage? And we actually came up with, and we proved the properties of it as well. We sort of established that this is the minimum, I'm not going to go through how we derived this. And so we established this, this parameter where we say the minimum, the log to the base 2 of the minimum of my distribution of the sequence where I am in. So I'm at this node, I'm going to compute my sequence, and if this node, and I establish this as my minimum, as if I know I have to exceed this value, and then I compare this with my threshold. I compare this with my threshold, and if my threshold is exceeding this, I say, okay, there's no point me even going because I've already established my flow because it's a monotonic function that we establish here. So I'm going to run through a couple of results as well, and then save us some time for questions in the end too. So then we said, okay, how do we, and we did multiple experiments with it in the paper. One is looking at how do we, can we predict it, right? So if this is my training and testing, and I'm trying to predict what would be the next sequence, if you will. If I take my ship movement graphic, if I build my first order network, this is what my first order network would look like. BA, you know, A to C, C to A, A to B. Given those three trajectories, I would say A is connect, you know, that's the sort of those connections that exist. My higher order network would tell me, and this is like a simulated toy example, just to make a point, that depending on where the conditional, I'm adding another layer, another node in my movement traffic. And now I'm going to make a prediction whether I go to BAB, what new trajectory would happen later. With the first order network, I get the first one correct, I get the others incorrect. And with the higher order network, we mostly get all of them correct. And then we can simulate many steps with this. And if we compare it with the, for the second order network, when we and for the first order, higher order net, and when I say second order, we're actually comparing with Roosevelt's algorithm. Whenever we have HON max order 2, that's our algorithm for higher order networks. And then we can compare the accuracy of these approaches, and as we're simulating multiple steps that go from there. So it does establish, and we have more empirical results in the paper for this approach. And then we had used 3 different data sets as well as to what kind of higher order dependencies we were able to explore were revealed. In the shipping network data, we revealed up to 5th order of higher order dependency. And as I said, so far all the work had assumed only first order exists, and all the analysis on the invasive species risk and the species flow movement, what ports pose a risk to what port, was conditioned on that first order network. When the actual risk and the species flow is demonstrating a 5th order dependency. And because we ignored that, now imagine the ramifications of, as we're working with ecologists and biologists, and especially now we are beginning to look at the Arctic region, where we have a Canadian collaborators collecting samples, and we are looking at what DNA, what species. In fact, they have a very cool technology where it's called eDNA, where they, from different ports in the world, we collect water samples. We run it through a sort of, for the lack of a better word, parchment paper. And so basically, and then they bring it to labs. So I can bring it from any port, as long as I have access to it, I can do that. I can put it in my bag, bring it back to Notre Dame, run it through a sequencing machine, and it tells me what species have visited that port within that water sample, just by doing that. So we can get of course, that also means that, you know, I'm from India. In Indian ports, you'll find everything that has ever lived in our ports, right? So you know, so it introduces a lot of noise as well, but at least we can get a good sense of that. And of course, and the other thing as well is only the species that have a corresponding, you know, sequence existing, because they're looking at a lookup table. So now we're doing the same thing in the Arctic region as well, is that as the shipping routes open up, what environmental risks are posing to the Arctic region. And if we apply the first order thinking, we would basically be this, most of the traffic is sort of even within the architect, one port to the other port as well. But the risks are coming from outside of the region, which we need to be able to capture as the ship movement happens. So we explored that. We found up to a third order on the clickstream data. These were the number of records that we had for both ship movement and that. And our observation of a third order agreed with the observations that Shetty et al. Had in their paper, where they looked at specifically the trajectory of clickstream behavior on these websites and how far people go before they find something. And they found there was up to a 3 order on Yahoo, and we sort of discovered the similar kind of a thing. And for retweet, we didn't have a complete network available, so we basically we didn't quite reveal some of the dependencies as well. So again, so one of the things that we do sort of have done is that either the existing approaches, so this is where sort of, our work in higher order networks has begun to make a difference, is existing approaches either ignore higher orders, so we work with the first order networks that we have, or we modify existing analysis algorithms, which cannot really generalize, and we're sort of tackling these issues, and hopefully, and that's what we have done with the higher order network representation, is that we have created an abstraction, a principled way, and also parameter and highly scalable, parameter-free and highly scalable way now to sort of build and abstract those dependencies and work with the existing algorithms. So this is sort of the invasive species application I'm going to talk about. Is so the way so this is the zebra mussels at Great Lakes, and these have caused, and there's enough newspaper articles about the damage caused by zebra mussels, and they can be traced back to where they came from. Same with Asian carp, etc. And they clog water pipes. They were attached to boats, etc. And not really good. So the way it sort of happens is that imagine a ship is leaving a port and it doesn't have a full cargo in it. So it's leaving Tokyo. It doesn't have full cargo in it. So it says, all right, I need to, for buoyancy, I need to basically get some water in my ballast. And the ship does. Hey, I'm at the port. I'll just take the water from the port, put it in my ballast. So it helps me with my voyage. It helps me with my balance. And then I will move on, right? So it's sort of, and as it's putting water in its ballast, any organism that may be in the port, even microorganism, sort of find a happy home in the ship's ballast, right? And then there's other ways as well. There's also these species get attached to the hull of the boats too. So it's not just the ballast, it's the hull of the boats as well. And then they sort of, go on during the voyage, and they move on from Tokyo to Singapore. The ballast tanks are full because the cargo is empty. And then they go to Singapore, and they bring in all our electronic devices, and they load up the cargo, and then they decide, hey, I'm loading cargo now, so I need to get to the ballast water. Of course, it's one ocean, right? What I got from Tokyo, I'll just empty in Singapore. It's just water going from one port to the other water. So I empty my ballast water, and then the species that were in Tokyo that may have entered the ballast are released with the water in Singapore. And now those species may find, and I'm just making up these two examples ecologically that may be relevant, but those species may find that the ecosystem of Singapore is fantastic for them. It's a great new home, right? Very hospitable environment. But the existing species of Singapore go, hang on, what just happened? We don't, invading in our ecosystem here. But the species from Tokyo thrive, multiply, and the species at Singapore go on a defensive mode, and as a result, the ecosystem gets perturbed from its original sense. So this is, and again, from a simple ship movement traffic, doing its business, carrying cargo, bringing in animate objects, and animate objects as well as a result, is causing us the challenge of this. And then the ship may even not fully empty the ballast water in Singapore, because it may only get as much cargo, may not have full cargo. So from Singapore, it may go to Busan, another port in Southeast Asia. And then it empties a little bit more ballast water there. Now, if I didn't know it came from Tokyo, I would think Singapore is posing a risk. But the risk actually, the ballast water was loaded up in Tokyo, not in Singapore. And that's the fundamental problem where first order networks are not able to capture with the ship movement traffic. So we did that as the example I already showed to you. And this was the clusters that we did. So there's a lot of Italians here, so you'll know this port. So we did a first order network, and we basically clustered it. So all the colors belong to the same cluster, and Valletta and Malta Freeport were in the same cluster as well, right? Because of the connections. Of course, one is a smaller inland, more of an inland port, and the other is a more connected port. Malta Freeport is more connected from that perspective. With the higher order networks, what we found was Valletta was in 2 clusters, because now with the higher order network, we can actually have multiple cluster memberships. And the Malta Freeport was member of a variety of different clusters, because the ships were transitioning from different ports of the world, coming into Malta, and then they may be directed more inside. And that's the problem that even Great Lakes have, is they are only about, I don't have the slides with me, but they get less than 1% of the world's shipping traffic in the Great Lakes. But they are about 4 or 5 steps away from every other port in the world. The ship may come, and then it sort of goes through the internal waterways and canals. So it's not those internal waterways and canals within the United States or North America that are posing a risk. From that perspective, it's where the ship originally came from. So if I just look at the internal waterways and canals and I build my network using those, I'm going to ignore the external influences from that perspective. So we are able to identify these clusters, and then we are working with our ecologists now to actually validate some of these things. So this is the challenge that I think is a challenge in science, right? So we can demonstrate these clusters, we can demonstrate this intuitively, and now the ecologists often wonder, how do we prove the species was invasive or the species already existed based on the DNA that we have done? Right? How do we know the origin of these species, some of these species that we are finding at some places? Some are documented, some are not. So how do we begin to build a data bank today to establish and do this analysis? And that's why the Arctic region is providing us with a pristine opportunity to begin this on step 1, because it has not been invaded to the extent, right? It has not been spread to the extent. So we also looked at the clickstream data. So from a big South Bend Tribune, the big media, the newspaper house in South Bend, we collected all their clickstream data, and they, WDB, and we basically the actions individuals took. So we know who came, what action they did, where they went from there. So we have the navigation patterns available to us. And the first order network sort of created something like this. The second order network created a more elaborate process where people took a couple of different steps when they went through the web pages. It was just not, I'm going between these pages, and there were dependencies where they came from, where they began. And when we demonstrated some of the page rank scores and how the page rank calculation changed the ranking of the pages, and when we sat down and talked about with some of the domain experts from the media side, they were surprised that some of the pages were getting such high rank scores using the first order network when they actually should have been losing. They shouldn't have been as high from that perspective. So, and more than 90% of the pages that using the first order lost their page rank scores from that on. And then again, this was the anomaly detection work that's under review right now. So if you think about what we're interested in, is patterns of anomalies over time, right, which could arise from trajectories of behavior online, etc. Now, if I look at this trajectory here, the first one, 8 a.m. to 9 a.m., 9 a.m. to 10 a.m., and if I just built my first order network, right, I go from soccer to weather to the television page, and I go from ski shoes to weather to paying some money, I guess, right? And I build that out. Even if you notice over here, my origin page, my destination page changed between 9 to 10 a.m. as compared to 8 to 9 a.m. Right? So my destination page actually changed, where I went to the TV page after coming to soccer, then going to my weather, and then going to TV, versus over here I was going to check out. My network will not change. Because from the weather, I either go to these 2 places. My network isn't changing. But if I look at my sequence, look at my trajectory, it's an anomalous pattern that I've observed. It's a change, may not be anomalous, it's a change of pattern from my 9 a.m. trajectory. Higher order networks are able to capture that something has changed in my dependent structure. I should pay notice to it. Is it a change point of my network? Has my network structure changed due to some external stimuli? Is it an anomalous pattern? Or is it what the new state of the network will be? We don't know, but we can monitor and observe, we can detect it, which we are not able to detect with the first order network because both these networks would look the same. Because if I just look at the patterns from this, twice I go to checkout, twice I go to TV. And I'll build my network this way. Twice I go from the soccer to this, twice I go from the ski boots to this. All right, I built my network, I'll do my analysis. No change between these 2 hours. But something has changed, clearly, if you look at the raw data. And if I don't have access to the raw data, if somebody give me this network representation, I'll go ahead and build my fanciest new algorithm using this network representation, arriving at a conclusion which may or may not be correct, right? So this is where building all these abstractions becomes very, very interesting. So we did this across a dynamic network where we started looking at what happens as we are giving a multiple sequences to these, and then when do we begin to notice that something has changed. So we played around with some second order patterns were emerging in this slide isn't working. In this section here, which the first order network believes nothing has changed in the graph at all. But there were some dependencies that were being introduced at time series 3 and time series 4. These dependencies, so until now, higher order network is behaving like the first order network because there was no dependence. Higher order HoN algorithm said there's nothing to go beyond first order, I'm just happy with it. Now at this stage, it notices something. At this stage, it notices something. So when it notices these things, is it a change point in the network, or is it an anomalous pattern? And does the network after this go back to this form, or it stays like this? Which means, has my network structure now changed, which is fine, or was it an anomaly that happened and then it goes back to its original form? So we did this using the Porter Taxi GPS data as well. And then in Porter, they have this burning of the festivals, ribbon festival, burning of in week 44. So there was multiple data points that were happening across my distribution. And this is HoN minus FON. This is the difference between the two distributions here. And the week 44 from the taxi trajectory data, so there is a peak over there that's observed with the higher order network based on the taxi trajectories that were observed. And we could, and what's the beauty of this data is we could precisely look at that week and say this event happened in Porto, Portugal, and there should have been some changes in the traffic patterns, some changes in the trajectories of taxi movement data. And we observed that with higher order network, and which is much more pronounced. It is not that pronounced with the first order network. So if we were looking at the network for anomalies, the point here is, of course, what we're trying to demonstrate is we are looking at this network to detect anomalies or changes. I would have missed it if I were to have just given you the data using the first order network representation. But there is a clear pattern that emerges during this time. And then we even plotted out the network as well. We looked at the police sessions at Porter. We looked at week 43, what is happening. And we looked at week 44, the patterns and the connections that were emerging in the data suddenly begin to look very different. And it is anomalous and not a change point, because then we go on to the next time stage and it goes back to the original state. So we're able to classify it as an anomalous behavior within our data patterns. So something else that we have been thinking about as well is that once we have built these things, how do I begin to visualize and interact with this, with the higher order networks, and how do we begin to display them? Because while our analysis algorithms are not changing, our visualization tools have to think differently to show these higher order dependencies, so I can interact with them. So along with the visualization faculty colleague of mine, Chawla Wong, and then we brought in the postdoc, Juntao, and we sort of started thinking about how do we begin to create a framework, and this was published earlier this year. Again, this software is also available to do this. So we looked at what we are trying to do. We are given this input data. We are trying to construct these networks, and we are trying to basically establish a visualization and interactive exploration. So from a invasive species perspective, we needed a geographic view. We needed, once we extract, so this algorithm exists. We can go from here to there. What was missing is, after this, we fed it to detect community detection, link prediction, or page rank algorithm. we couldn't explore, we couldn't play with the data to see what's going on. Why is this phenomena existing? What's causing these dependencies? Where they're coming from? So we have created multiple dependencies views where we can look at a global view of the data, we can look at individual nodes, and then I can select a region and look at how the flows are happening in the region within the tool. And I'm not a visualization person. I have no sense of visualization, but I believe my colleagues do. So, so this is sort of, the table view that we had, and it's not displaying as crisply here. So we basically can look at, so that if you follow the mouse, I can look at a particular node, say Salvador, Santos, etc., the connection. I can select a node over there and break it down as to where the connections are happening, what the higher order dependencies may be, and I can see what the diffusion patterns are for this region. So let's say if I want to look, I can pick any node and I can say, okay, what are the risk dependencies to this port from what other ports in the world? I can begin to look at this network and I can trace it. I can plot it out. I can see what ports are of impact, and I can even place some scenarios where if I introduce this port in the mix, what's going to happen? How is the network going to rewire? So from an architect perspective, we are able to play these war game exercises or scenarios where we inject these nodes in the network in the dependency structures. Then we say, okay, what risks are spawning off based on these interactions? So, so that's where our visualization toolkit. And again, to summarize, really, so as I talked about, we think about applications, but we sort of ground ourselves back and thinking, okay, what are some of the algorithmic or methodological work that we can do? So we have the higher order network, and the HON plus only difference being is this becomes parameter free and more scalable. We have looked at different applications, whether we have from clustering to the shipping network, for example, ranking, the clickstream behavior, for example, anomaly detection, and as well as looking at what's the right visualization framework to do this work. And this is the website that you can go to, and Jianshu, that's my student now. For some reason, he went to banking after his PhD too. So that's the this is the website here, and he believes video should be good for everything, so we have a video, and it has a British accent to it, even better. Right. So and then so the code is here, and these are the papers that we was talking about. This was the first paper. That was in Science Advances last year. This was the visualization work that we published earlier this year in the spring. And then we have and then we also have a couple of other papers on this. And then the anomaly detection paper is on online, but the source code is representative of the new approach. Right. Well, thank you, and I can take questions now. Yeah.
So often, so you show that you can start from the traces of activity and go to your representation of desire of the network. But often we'd like to do the opposite. We start from aggregated patterns, and we do not have access to the traces. A good example is in browsing, when you have aggregate snapshots that can be more or less safely released without huge privacy concerns, whereas if you share the actual steps each individual takes, that would be a huge privacy problem. Do you have any idea?
I don't. So basically what you're saying is that we're given a network, and that's what we know about the world, right? And we don't know if the network is a correct representation or an incorrect representation. We don't know how to answer that question today. What we are relying on is that I'm given some raw data, whether it's my data collected from actual click streams that I'm getting, the dump we are getting, or we are getting it from the movement traffic or cell phone cascades, and from there we're trying to build these networks. So we are relying on availability of the raw data. And I don't know yet as to how do I infer whether the first order network representation or whatever network representation I have is a correct representation of the underlying world. I don't have an answer. as yet.
So kind of a follow-up to that question, I think in a lot more common senses is that we don't have these trajectories of ordered node sequences, but we might have a sets of nodes that have higher order correlations between them. So do you have any ideas or maybe like a random walk on that saying might be applicable here?
So what we're looking at is we're looking at some of the biological networks and healthcare applications where you don't quite have these, but there are these other functional relationships that exist, and we are trying to see if we can develop and explore some of these things out. So yes, that's something that we're looking at quite actively, and we're looking at it from that biomedical application side. Yes.
So the examples that you used had pretty much continuous data, right? So they're, I mean, in a practical sense, right? So they're over time, and you have lots of different time points that you're talking about. I'm wondering from a standpoint of a social scientist who might have a few waves of data, if this actually could be used that, or if there's actually some practical implications for your model or assumptions behind it that require that you have evenly spaced time element for time frames, or if you need to have at least an X number of times in which you've collected the data on the network in order to be able to propose this.
So there is no requirement on that this being at equally time spaced or something. All we're talking about is exactly the set answer I gave is there's a sequence, there's a trajectory that exists. The trajectory could be once every few years, once every day, or something, but there is that form of A to B to C to D, etc. There is a progression available. And that's what when we're looking at progression of diseases, etc. There's a progression available, doesn't matter what the time span is. And that's what we're looking at. So we have looked at it we built this from a cell phone communication data, where we said, okay, every 2 seconds, build out a network, which looks different. Every hour, every day, every week, it doesn't matter. Of course, the underlying networks that's discovered with the higher orders is very different when we change the time interval. But if you only have the 1 week time gap, it doesn't matter. So when we collected the photo data, they were spread over 44 weeks only for a snap of 46 weeks, 48 weeks, and whatever interval they gave us from the taxi data set, that's the interval we used from that perspective. So it's not really a continuous injected real stream. It's the observed data that we have. That's the only assumption that this algorithm makes.
So I'm going to follow up on Ann's question. So we've been working on the issue of pathways to care and thinking about that, and we've tried a number of models, and they all seem to sort of fall apart when you start talking about assumptions. So the last one we used was sequential multinomial logits analysis, and the problem in that was that at every stage you had to be able to go back to every possible option. Does this have any assumptions like that, like you can't go back to a port, or that you can you go back to a port?
Yes, you can go back to a port.
Okay.
You can go back to, absolutely.
And does the n that you have to increase dramatically as you have option numbers or port numbers?
So if the more original nodes there are, so it's basically conditioned on, because if there's more number of nodes I begin with, or if there's more number of dependencies in your care pathways, then I'm exploring their possible their dependencies, right? So yes, it's going to increase on the basis of the underlying n.
It's going to increase the number of sequence types.
But it's also going to, so basically it's not increasing your raw data, your actual n, actual number of ports, but it's basically saying, okay, if there's more dependencies that are existing, depending on, say in your thing, if it could be these 3 people were part of the care pathway, it was good to have that. Or if you look at the handoff network, for example, in a hospital setting, depending on what those handoff network was, those 1 to 2, 2 to 3, 3 to 4, if those are represented, then yes, then your number of nodes is going to increase. But it's only 1, 2 handoffs, then it's not going to increase.
You mentioned the Twitter, the retweets data set, and I was wondering how would that work, because Twitter usually gives you, so if you're looking at retweets, even if A retweets B and B retweets C, Twitter only gives you the direct link.
Yeah, so that's why if in that table, I had it as non-applicable because we didn't have the network. So that was that.
Yes, I was hoping.
For you, I had that result here. Because I knew this would come.
technical question here. So you talked about setting a threshold for determining the order score. And ideally, the threshold would be like based on the KL divergence and you assume from statistical significance.
So we basically have said we calculate a support parameter, and we basically, okay, this is the depth, this is the support parameter we'll go to, and that's the sort of the delta we compute as a threshold. And then we say, okay, is this threshold, when we compute a KL divergence, is it exceeding or beating that threshold?
And the threshold is computed for that network, right?
Yes.
No,
Based on that network properties. But it's the same equation that's used, but it's computed based on the data.
If I'm applying it for a different network, I compute a different
Yeah.
threshold.
And follow that up, I would imagine the parameter-free versions, so does it try to set that automatically?
So the parameter-free version basically it converts, yes, finds a threshold automatically, but what it's basically saying, what it's basically doing is that because it's establishing the minimum support from the log to the base to min of the probability, we're saying, okay, if that is not exceeding the threshold, we just stop there. But we still need, the threshold is computed from the data because based on the standard equation, but we are not setting any minimum support and minimum this and minimum subcount parameters because that was something that we had to set. And we had to show that parameter sensitivity in our first paper as well, which is the point that reviewers really, for the first reviews, said, show me the sensitivity of that. And that's what we try to stress on.
Well, I think we're out of time, but Dr. Chawla has agreed to hang around a little bit for a reception, so you're all welcome. I believe food has been delivered. I can't see it from here.
Yes.
So please spend some time with us and you can talk more about it. Thank you so much.
Thank you.